Hi everybody. Today we're going to finish off on our third day of angle identities. And so what we're going to look to do is by the end of this lesson we're going to add in 4 more angle identities, and we're also going to see some instances where we can use them. So what I'd like you to take a look at is the screen right now. And given what you see on the screen, this should be a good opportunity to go through and see, did you pick up what you needed to from the previous lesson? So I'd like everybody to pause the video, give A a shot. If you are super comfortable, then work your way through A and B as well, and we should match up in the end. Okay, and we should be back then. So when we take a look at that first one, we should be good then to be able to go through and say, if I was to think of that 7/12 as a 4/12 plus a 3/12, then 4/12 would reduce to 1/3, so a pi by 3, and 3/12 would reduce to a pi by 4, a quarter. Then we could break that into special triangles and be able to then apply our compound. So cos of the first, cos of the second, opposite sine, sine of the first, sine of the second. Once we have that, then we should be good to be able to use our special triangles. And so now we can deal with pi by 3 as big angle, which means it has a big opposite side, which means it has a small adjacent side. My cos. Now I have my sine of pi by 3, big angle, big opposite side. And my pi by 4s I'm pretty solid with. I can then reduce and rationalize. Yikes. And we should get down to that same thing. So hopefully we matched up. If we were a little unsure and we wanted to check after A, then let's do the same thing and let's pause the video now and work our way through B. Okay, we should be back. I believe last time I went through and I viewed this as a 9/12 plus a 2/12. So today, just to mix things up, I'm going to view 11/12 as an 8/12 or 2/3 and a 3/12 a 1/4. And so when I break that up, I have sine of the first, cos of the second, same sign in between, cos of the first, sine of the second. This was an instance where we were dealing with an angle 2 pi by 3 that was not in the first quadrant. So maybe I went through and I drew on a special triangle just so I could remember that that adjacent side had to be negative. Now I can go through and I can find all my values. So my sine of that is going to be root 3 over 2. My cos of pi by 4, I'm really solid with. My cos of 2 pi by, and there would have been the common mistake, forgetting that one to be a negative. And now we can simplify and rationalize. And so if we got down to match up with those two problems, then I think you can take away that you understood what you needed to from the previous lesson. Okay, let's jump into some new stuff for today. And so you'll notice when you take a look at that screen that we're about to introduce our 9th new angle identity. And what you see on the screen is your tan compound angle identity. And just the same as the previous, for us to be able to use it, we got to be able to prove it. So this may be an instance where you want to pause the video and give it a shot. See what you can come up with. If you're feeling very confident, then I would argue give that a go. Otherwise, you hang tight and we'll walk through this one together. So pause the video now. Okay, and we should be back. So the first thing I would maybe want to highlight is when we take a look at this, I think I would want to manipulate that right side first. The reason for it is that I have so much stuff on the right side. And everywhere that I see a tan, I know that a tan is equal to a sine over a cos. So when I see the tan of A, I know that that could be written as sine A over cos A. Same thing with the tan of B, that would be a sine B over cos B. That would all be over 1 minus, and I can make the same substitutions on the bottom. Notice I'm subbing in on brackets on the bottom because I see that I would have multiplication between my tan A and my tan B. Okay, every time I sub something in, now I go through and I try to simplify. So on the top of my overall fraction, that big fraction line, I notice that I'm adding 2 fractions up here. And if I'm going to add together 2 fractions, I need a common denominator. And so that common denominator could be found by multiplying together the 2 denominators. Now I'm kind of playing that game of what did I do to the bottom, I do to the top. So in the first fraction, I multiplied the bottom by cos B, so I need to multiply the top by cos B. In the second fraction, I multiplied the bottom by cos A, so I need to multiply the top by cos A. Okay, on the bottom, well, at the very least, maybe what I might do is I might just simplify. And if we're going really cautious, then maybe that would be your first line on the denominator. However, I think, as we're taking a look at that denominator now, we could see where we would go next because we're not fully simplified. That now we're trying to take 1 and subtract a big ugly fraction, and to subtract fractions we get a common denominator. We could skip that step. I don't think that it's too much for us to look instead up at this line and say, we can see that we're going to multiply these 2 fractions together, and you're going to get a denominator of cos A cos B. You're then going to have to subtract it from 1. So instead, why don't we go straight to our common denominator of cos A cos B and change 1 into that common denominator, and then simplify the top by multiplying our numerators together, and we can come in on that line in one go. Okay, we have simplified the top and the bottom of the big fraction line fully. But we do have the opportunity to be able to go through and deal with this big fraction line. Now, we could view this problem as I have a fraction on top divided by a fraction on the bottom, and divide fractions means I flip and multiply. Now, I'm just going to write this down very quickly because I think after a little bit of practice, we may be able to avoid this line when we see something arise. Do you notice that when we go through to multiply those 2 fractions, your cos A cos B's will divide out as common factors? So, can we maybe skip that big ugly line that I wrote down in a really sloppy way? And instead, let's look back to the previous line. I notice that my top is divided by cos A cos B. My bottom is divided by cos A cos B. And so, if instead I multiplied the top of that fraction by cos A cos B, and I multiply the bottom of that fraction by cos A cos B, I can see that the purple means I really just multiplied by 1. So I didn't change the value of the fraction. But by multiplying by 1, that form of 1, those denominators will multiply out. So, you never have to show me that big purple line Instead, if we see that we have the same denominators on both, then let's just multiply them out. Of course, if you're not comfortable, we can always flip and multiply, and we'll get down to the same thing. What we do arrive at then, a little quicker, is sine A cos B plus sine B cos A all over cos A cos B minus sine A sine B. Now, for some of us, we're going to stop there. And we're going to hit a snag because we cannot simplify further. And maybe then we jump over and we start dealing with the left side because we know that tan of A plus B could also be written as sine of A plus B over cos of A plus B. And now we could use our compound angle identities to break down both the top and the bottom. However, can we look at the right side again and notice that if we look up at this numerator, that takes a certain pattern to us. We have sine of one angle, cos of the other one. Then we add to that the sine of the second angle and the cos of the first one. And we may notice that that is your compound angle identity for sine. So I could break that and almost rewrite it as an unbroken down compound angle, that I'm dealing with angle A and angle B. Thing I need to focus in on right now, I know that my sine compound angle identity always has the same sign in between. Okay, I take a look at my denominator. My denominator is a little easier to see because I have cos of an angle, sine of an angle, sine of an angle. And I know that that matches up with my cos angle identity. When I take a look at the sign in between, I know that my cos compound angle identity always has the opposite sign in between. So since the bottom has a minus in between, its compound must have been addition. And if I have that, then I can go backwards because I know that if I have the sine over cos of any angle, that is equal to the tan of that angle. And there is our proof. So, now that we've proven that identity, we can use that identity anytime we like. So, let's use it to find something useful. Take a look at the screen now, and what you'll notice is we're going to add in, if you want, the second half of our tan compound angle identity. This should be very fast for us. I'm going to go through it as if we're all going through it together. We've gone through dealing with the negative case many times now. So I know that what I can do is I can view that as one angle added to the negative version of the other angle. Well, now I'm going to use the previous tan compound angle identity for addition to break that down. That's going to give me tan of A plus tan of negative B all over 1 minus tan of A times tan of negative B. And just like previously, the original statement did not have negative angles in it, so now I need to remove my negative angles. So I'm going to apply my tan negative angle identity. I know that the tan of any negative angle is equal to the negative tan of the positive. And so where I see my negative tan B, I can replace that with a positive tan B as long as I make the term negative. On the denominator, I can do the same thing. But since I'm going to now replace this with a positive angle, this ratio would be negative, and therefore the sign in between becomes positive. And there we go. So we now have both versions for us, and I want to make sure that we've got them both where we can know them cold. So what I'm going to do is I'm just going to write beside our tan negative angle identity our tan positive one. And so beside, if we had tan A plus B, we would have a similar breakdown. And so what we want to see, both when we break down tan, is tan of the first, tan of the second. What sign goes in between those? Sorry, I just shrunk that on you. We may notice it's the same sign in between. Now, what's on the bottom? We have 1, and then you may notice that it's the opposite sign of what you put on top. And now we have the product. So follow along with either one of these and you'll notice our pattern. It's tan of the first, same sign in between, tan of the second, divided by 1 opposite sign, tan of the first times tan of the second. And now we've finished off our 9th angle identity. We now know our compound angles for tan. Okay, let's add that one to the pile, and we're going to add a bunch more. If you take a look at the screen now, you'll notice that what we're going to do is we're going to add in double angle identities. And so the instruction on problem 4 is simply to discover identical identities for, and we're going to walk through all 3. So you'll take a look at the first one. Why is this called a double angle identity? Because you'll notice that whatever angle x is, we've doubled it inside of our ratio. Now, I would normally give us a bunch of time to work through this and try to stumble upon it. That's why I gave you the instruction discover. These ones happen to be, in my opinion, the easiest identities for us to prove because we've already got what we need in our background. That if we can view 2x as x plus x, then you can view that double angle as simply the addition of 2 angles that are the same. And if you can view it as the addition of 2 angles, well, you know how to break down your compound angle identity. And so when we break it down, we have sine of the first, cos of the second, same sign in between, cos of the first, sine of the second. The only issue before was we could never simplify that because we always had different angles. Well, now we have the same angles. And you'll notice that in that breakdown of those 2 terms, those are 2 identical terms. So to add those 2 things together, we get 2 sin x cos x. And therefore, you now have a double angle identity. That the sine of any double angle is equal to 2 times the sine of the single angle, cos of the single angle. We just added in your 10th identity. Let's add in 2 more. And so if you take a look at the screen right now, I would like everyone to work through these on your own. You now know how to get down to discovering double angle identities. I'd like to let you go and see if we can match up with the same thing. So let's get everybody to pause the video right now and give it a shot. And so we're back. And then if I take a look at that first one, I know that I can view cos 2x as cos x plus x. And therefore, I can break it down into the cos of the first times cos of the second minus sine of the first times sine of the second. And when I simplify that, I'm taking a cos x times a cos x, so that's something times itself, so it's squared. And same thing in the second term. This is going to be a version that I want you to hold on to. Now, what I'm going to ask you to do, leave a little bit of space on here. because I want to come back to that cos double angle identity, and I want to address a special situation that we can deal with in that one that can be helpful. So let's jump over to C then. I know that I can view the tan of that double as an angle plus itself. And if that is the case, then I can break it down using my compound angle identity. My tan identity is tan of the first, same sign in between, tan of the second, all over, one opposite sign in between, tan of the first times tan of the second. And if we have that, then we can go through and we can simplify. On the top, you have tan x plus tan x, so we have two tan x's. And on the denominator, you have a tan x times a tan x. That would be our tan squared. So this is the version. There is our double angle identity for tan. If you had to remember one version for each of those, then those ones with the purple star beside them are the ones you want to know. The tan one, that one is in your back pocket. The cos one, I want to walk through two other versions of that identity. If I had to remember one of them, it would be the purple star. But it can be helpful to know two others. So let's jump back into grade 11 a little bit and see that you do have your Pythagorean identity. That you know that sine squared x plus cos squared x equals 1. And therefore, you know that you have the other manipulations of that. That you know that sine squared is going to equal 1 minus cos squared, or cos squared is going to equal 1 minus sine squared. And so, if I were to use those in the substitutions, so let's go back to that purple starred form, the cos squared x minus sine squared x, and let's write that entirely in terms of sine. So that means I want to get rid of my cos. Well, to get rid of cos, I know that cos squared is equal to 1 minus sine squared. And so I could replace that with 1 minus sine squared. And I could then simplify that to 1 minus 2 sine squared x. This is another version of your cos double angle identity. And if we were to do the same thing, but now I would want to get rid of my sine and write it all in terms of cos. Well, then I could do the same thing. I could go back up to the purple star, and I could keep the cos squared in, but now I want to get rid of the sine squared. So I'm going to replace that sine squared with 1 minus cos squared. When I simplify that, I can see that I'm going to have a positive cos squared with the other cos squared is going to give me 2 cos squareds, and then my negative 1 when I expand. There is another version of your cos double angle identity. So you have 3 versions for your cos. If I had to work to remember one of them, it would be the purple star. However, as I said, the yellow star and the blue star can be useful forms. But you can see that if you remembered the purple star one, you could always work your way backwards to either of the other forms. Okay, we just added in our 12th angle identity. As we add in these two, we are up to 12 now. That is all the new angle identities that you're going to be introduced to this year. So now what we want to do is we want to have them all in our back pocket, and we want to be really good using them. So let's jump in and see a case where we can use these. Okay, you take a look at question 5 on the screen, and it should look somewhat familiar. You're used to seeing problems by now that take this beginning. If cos x equals negative 3/5, and there's the location of x, find, well, now that we've introduced double angles, let's work our way through applying those double angle identities. So as you take a look at A, B, and C, I'd like you to be able to go through and come up with the values of sine 2x, cos 2x, and tan 2x. I think we should be comfortable enough to at least give this one a shot. So pause the video now, give it a try. Okay, we're back. So what I want to do is I want to walk through the first one, for instance. So if we were a little nervous about jumping in, then maybe if I was going to play around with my problem A, coming up with the sine of 2x. Okay, what I have in the problem pertains to angle x. And so I don't like having double angles in there. And so I want to switch it into a single angle. Well, I can apply then my double angle formula, and I know that the sine of 2x is equal to 2 sine x cos x. Now I've broken it into single angles, just angle x. So right off the bat then, I know that I've got 2. I don't know what sine x is, but I do know that cos x is negative 3/5. So if I could come up with the value of sine x, then I could find the value of the problem. Okay, some of us aren't even stumbling at this point because they can already see where we're going to go with this. That is, as soon as you were told that angle x exists in the third quadrant, you may have drawn on a terminal arm. As soon as you were told that cos x is negative 3/5, then you know the adjacent and hypotenuse. You could then go through and find your opposite side. Now, for some of us, we may remember our 3, 4, 5 Pythagorean triple, or we found that side because we knew that it was the hypotenuse squared minus the other side squared. So my a squared was 16, therefore my a was 4. I just had to remember it was a negative 4 because we're in the third quadrant. That's what allows you then to say that the sine is negative 4/5. We can then calculate that. My top's going to be a positive, and I've got 24. My bottom, when I multiply, there's my 25, and we are done. There we go. So, if you were a little nervous about jumping into that problem, I think we should be good to now go through and deal with B and C. So, pause the video now, and let's finish off those last two problems. Okay, and we should be back. So, I'm going to work my way through question B, and I just want you to notice that if we had gone through and solved A first, then we're probably going through and doing something like this. Okay, well, I know that my cos 2x is equal to cos squared x minus sine squared x. Okay, well, then I can take what I see on my diagram, and I know that my cos squared would be my cos, negative 3/5 squared, minus my sine squared would be my negative 4/5 squared, and now I could calculate. And so I'm going to square the top and the bottom, square the top and the bottom. I have common denominators, so when I collect, I get down to my negative 7/25. However, what I want to walk through is an alternate way to solve this problem. And what I want you to imagine is that this diagram doesn't exist. Imagine a situation where I gave you this context and I told you that cos x equals negative 3/5, and I jumped straight to question B that said, find the cos of 2x. I want you to notice that I need that diagram to be able to come up with my sine value, because my sine value was never given in the problem. However, if I broke down my cos 2x, rather than using my basic form, cos squared minus sine squared, but instead said, I want to break it down into my cos version. Well, for me to break down cos 2x, then that's equal to 2 cos squared x minus 1. The way I remember which version it is since I have coses in the original, then my 2 cos squared comes first. The other form that I have to try to debate between was, well, was it a 1 minus the 2 cos squared? No. Because my original was coses, if I want to put the 1 first, that makes the sines go second. That's just how I remember it. Could be a useful device. So we get to that point, and if I broke it down that way then, well, now I never need to know what the sine is. I can simply sub in the information that was given, and I never need the diagram. I square my negative 3/5. Now I simplify. Well, then that's an 18/25 minus, and my 1 would be like a 25/25. And instead, I come in on the same value. So just something to keep in mind as we move forward. And so now we should be able to work our way through the last one, make sure that we match up. We've got our tan double angle identity. Well, that one is 2 times the tan of x all over 1 minus tan squared. Now that I have that, I can simplify it. So I'm going to take 2, and then I have to multiply that by my opposite over adjacent, all over 1 minus, now I have tan squared, so there's my opposite over my adjacent squared. Some people will come right in on this line and say that I know the top would have been 8/3, and maybe they come in on this as their denominator. I think that that's a good line to come in on. You're not skipping too much. And if you do make a mistake, we can probably find it quickly. Now that we have that, I need to simplify my denominator, which means let's get a common denominator. My 1 will be 9/9, so when I subtract them, I'm going to get negative 7/9. Now I'm dividing fractions, so I'm going to flip and multiply. So when I multiply by the reciprocal, I'm going to notice that my 3 will divide out as a common factor. And so I'm going to get an answer of 24/7, and I need to make sure it's negative. There we go. So there is us adding in 4 more identities today for angles, and then getting a chance to work through some of our double angles. You know your job. Jump in, get some practice, make sure that we're pretty comfortable with it. Good luck.